Good afternoon, everyone. So, welcome to my YouTube channel, Math Saptara. Today, we are going to see 8th practice set on functions of bounded variation. So, let's start today's session now. Question number 1 is f be a continuously differentiable function on closed interval AB. Which of the following statement is correct? Okay. First option is derivative of f is continuous. Derivative of f is unbounded. C option is f is function of bounded variation. Options A and C are correct. Okay. Option number D is options A and C are correct. So let's see. What is continuously differentiable function? What is continuously differentiable function? F is continuously differentiable if derivative of f exists and f dash is continuous. Okay. So here derivative is continuous. Option number A is correct. And another thing is that we know that f dash exists. Sorry, f dash is continuous on closed interval AB. Is continuous because f is continuously differentiable. So derivative exists and it is continuous. Now derivative is continuous on closed interval AB. So this implies that f dash is bounded on AB. Okay. So now we know that if f dash exists and bounded on AB, then f is function of bounded variation. Okay. This derivation I have done. This if a derivative exists and bounded, then f is function of bounded. We have already done such function because such function turns out to be Lipschitz function, and Lipschitz functions are functions of bounded variation. So option number C is also correct. So option A and C is correct. Okay. A or C correct. So option number D is correct. Okay. Now see this question. F B contains a differentiable function. Which of the following statement is correct? That variation function x is given by integral a to x derivative of ft absolute value dt. Variation of f is equal to ab integral absolute value f dash derivative dt. F variation is not equal to integration a to b f derivative at t absolute value dt. Options A and B are correct. Okay. Options A and B are correct. Okay. Solution. Now, f close interval a b to r is continuously differentiable. If it is continuously differentiable, this implies f is differentiable. If f is differentiable, because derivative exists and it is continuous. Differentiable. So this implies f is continuous. Okay. Let P be a partition of AB. Okay. Then PB and P is this A naught x1, x1, x2, xn is equal to B. Okay. Xn is equal to B. And now we know that what is this? SP. SPF is summation I goes to 1 to n fxi minus fxi minus 1. Okay. Okay. But why mean value theorem? By mean value theorem, because function derivative exists. So by mean value theorem, it will be equal to summation I goes to 1 and what will be this? This will be f dash ji I, okay, ji I and xi minus fi minus 1 by mean value theorem. Okay. So I can write xi minus 1 is equal to delta xi. Okay. So what I will get? I will get this one. I goes to 1 to n derivative at ji I and this is delta xi because this is greater. Xi is greater than xi minus 1. So this is taking absolute value at delta xi will not affect anything. Okay. So what I got this one. SPF. Let's say equation number 1. Now letting non-p tends to 0, we get from 1. What we get? We know that limit. What is? We know that FAB is equal to limit non-p tending to 0 SPF. Because function is contains differentiable, contains function differentiable function of bounded variation. Okay. Now what is this? Delta xi. Now this function is Riemann integrable and norm is tending to 0. Now Riemann integrability, you see that this type of partial, this type of summation show the integral. So this is nothing but this, so this is nothing but this is equal to A to B F dash D dt. Okay. So we got BFAB is equal to this. Okay. Since F is function of bounded variation on AB, this implies F is also function of bounded variation on AX, where X belongs to closed interval AB. Now F is functions of bounded variation of this interval A. So following similar proof as above, we get what we get. BF A to X is A to X F dash T dt. But this function is nothing but variation function. So this function is nothing but this is nothing but BFX. So we got this. Okay. So which options are correct? Let's see. First option is correct and B option is correct. A option is correct, B option is correct. C option is not correct. So option number A and B are correct. So option number D is correct. Okay. Option number D is correct. Let Fn be a function of bounded variation for each n belongs to n, such that limit inferior, it means limit inferior is finite. Oh, this sequence. Okay. Limit inferior is finite. If Fn tending to F point-wise on AB, then which of the following statement are correct? First option is F is not function of bounded variation on AB. F is function of bounded variation. Okay. And its variation is less than limit inferior. C option is F is bounded on AB. Options B and C are correct. So let's check it. Okay. So limit inferior means what? Limit inferior means what? I am taking supremum of n belongs to n, infimum of this an plus 1, an plus 2 up to this sequence. Okay. Okay. Now, now this is given. This is, I am saying, let's say this is L. L is finite. It is given. Okay. Let epsilon greater than 0. Epsilon. Okay. Then there exists a subsequence F and K such that, sorry, one, what is this? Actually, I should write here this one. This is limit inferior. I'm taking of F and sequences. Limit infimum of B, F, and A, B. Okay. B, F, and A, B is equal to this. So this is supremum of infimum. So what's that? Fn plus 1, Fn plus 2, like this. Okay. So it is given that this is finite. If this is finite, you take any epsilon, there exists a sequence, a subsequent Fn k such that B, F, N, K, A, B is less than L plus epsilon. Okay. Okay. Let P is equal to A x naught, x1, x2, xn minus 1, xn is equal to B, B a partition of closed interval A, B. Okay. Then S, P, F, and K will be less than B, F, and K, A, B. Okay. That is less than L plus F. Okay. But what is this? This is summation. What is this? This is summation. I goes to 1 to N, F, N, K, X, I minus F, N, K, X, I minus 1. Okay. So this is less than L. Okay. Because you can skip it. Because if this is less than L plus epsilon, so this will be also less than epsilon. Okay. Now, letting Nk tending to infinity, we get what we get, because each is converging pointwise. It is converging pointwise. So we have I goes to 1 to N, F x I minus F x I minus 1, because it is converging pointwise. But it will be now less than sign will come, because it can approach, it can be, limit can be L plus epsilon also. Okay. So what is this? This is SPF. But this is finite. So this implies this is finite. So primum P belongs to rho A B SPF, that is less than L plus epsilon, and that is finite. So what does it mean? It means supremum P belongs to rho A B SPF exists in R. So this implies F is function of bounded variation. Okay. Now let's say this is equation number 2. Now from equation 2, from 2, we have, because what is this? We have supremum P belongs to rho A B S P F is less than L plus epsilon. Now what is this? What is this? This is nothing but BF AB less than L plus epsilon. Now epsilon greater than 0 is arbitrary. We get BFAB is less than L. But what is L? What is L? L is, put the value of L here. BFAB is less than equal to limit inferior of B, F, and AB. So this is, so which option is correct? Okay. So here, sorry, I forgot to write here. Actually, this is, I forgot to write here. This is limit inferior of. So write it again. So what is the meaning of BFN? So BFN means BFN means BFN AB. So what is it? Supremum of N belongs to N, infimum of BFN BFN plus 1. Okay, like that. This sequence. You can write one more term here also. BFN plus 2 and so on. Okay. So which options are correct? First, F is not correct because it is function, F is function of bounded variation. So second option is correct, and every function of bounded variation is bounded. So option B and C are correct. So option D is correct. Okay. So question number 4. Let F, I am for each function of bounded variation on closed interval AB, I am writing norm F. It is called two vertical lines. It is called norm of F is equal to absolute value of F plus variation of F. For each F and G belongs to function of bounded variation set, and alpha belongs to R, which of the following statements is correct? F is 0 if norm of F is 0 if and only F is 0. Norm of alpha F is absolute value times norm of F. Norm of F plus G is less than norm of F plus norm of G. D option is all options are correct. So let's see its solution. So option F, norm of F is 0 if and only if F is 0. Let's check it. Now if F is 0, first let's, if F is 0, then what will be the FA? FA will be 0. And this is a constant function. So variation of FAB will also be 0. So this implies norm of F is equal to 0 plus 0, that is 0. Okay. Now conversely, if norm of F 0, this is, but norm of F is equal to norm of absolute value of FA plus variation of FAB. So this implies absolute value, this is 0, and variation FAB is equal to 0. So what does it mean? FA is equal to 0. And what is the meaning of this? If variation is 0, this implies F is constant. F is constant. Okay. Okay. Now I will calculate what is the value of F constant, because it means this will imply FA will also C, but this is 0. So C is 0. So this implies F is 0. So first option is correct. Now see B option. B option is alpha times F is equal to absolute value F of norm of F. Okay. Now what is alpha F? This is absolute value of F A plus variation of alpha F A B. So what is this? Alpha F A. How can I write this? Okay, let's expand it properly. Okay, what is this? This is alpha F A plus variation. Variation of alpha F is nothing but absolute value of variation F A B. But what is this? Alpha, I can write this. Okay. So what is, you can take alpha common. Absolute value alpha, you can take common. So what is this? This is nothing but alpha norm of F. So what we got? Norm of alpha F is equal to, okay. So option number B is also correct. So option number B is also correct. Now check option number C. C. Now what is F plus G? This is F A, F plus G plus variation of F plus G A B. So what is this? This is F A plus G A. Okay. And I know that variation of F plus G always less than variation of F plus variation of G. Okay. So this is greater than equal to this part is greater. And this is also greater than, this is also greater than this part. Okay. So this is finally this. Okay. So what can I write this? F A plus variation of F A B. You combine this part plus variation of G A VG AB. So what is this and what is this? This is norm F and this is norm G. So this is norm F plus norm G. Okay. So this implies norm of F plus G is less than norm of F plus norm of G. Okay. So C option is also correct. So which option is correct? A option is correct, B option is correct, C option is correct, D option. So therefore all the options are correct. So option number D is correct. Okay. Now move to last question. This one. So F, I am taking norm of F and I am defining a distance function D. That is norm of F minus G for all F G belongs to BAB. Okay, then BAB is a real vector space. Okay, BAB is a metric space with D is a metric on that, and BBAB is a norm space. Okay, so solution. You can check that first option is correct. BB, what is this? BAB. Actually, what is the BAB? You are taking F function from closed interval AB to R. F is function of bounded variation on AB. You can check that. It is easy to verify that it is easy to verify that BAB is a real vector. Real vector means you are taking real field. You are taking field real number system. Okay, so it is a real vector space. You can check it, no problem. It is easy to verify. Now, second option is it is a metric space. Metric space. Yes, this is a metric space. Why? You can check this is a metric space. Okay, it is also to verify that it is a metric space. Second option, second, it is routine to verify or easy to verify it is easy to verify that BBABD is a metric space. Okay. Only thing is that we have to verify whether this metric is complete or not. Okay. So now we claim that this is complete metric space. Metric space you can check. It is easy to verify. So let Fm be a Cauchy sequence in BBABD. Okay. Okay. Let epsilon greater than 0 then there exists cap there exists capital N belongs to M such that D F N F is less than epsilon by 2 for all N greater than equal to capital M. Okay. Now what is DFN? DFN is nothing but this non Fn minus F. So this is less than epsilon by 2. But what is this actually? This is non Fn minus F is nothing but equal to Fn A minus Fa plus Bfn minus F A B. This is less than epsilon by 2 for all and greater than capital N. Okay. But we know that, so this implies, but we know that, so this implies Fn A minus Fa, because this quantity is less than this quantity whole quantity, so this will be also less than epsilon. And what is this? This will be Bfn minus F A B is less than epsilon by 2, because these are non-negative quantity both, so they are lesser one, so they will be also. But this is always less than Bfn minus F A x. X is belonging to closed intervals, and this is also less than Fx minus Fa. Okay. This is for all n greater than. Okay. And X belongs to closed interval AB. Now what is the meaning of this? Now Fna, sorry, this is nothing but F1. I made a mistake. Let me check it again. So this is Cauchy. This is a Cauchy sequence. This is Fm. Fm is here. This is Fm. Okay. Fm. This is Fn. Fm. N and M greater than N. M and N greater than N. M is also here. Okay. Okay. Now this is, we have Fa minus Fm A less than epsilon by 2 for all n m n greater than n. So what does it mean? It means this implies Fn is Cauchy. Fna is Cauchy. Fna is Cauchy sequence in R. So every Cauchy sequence converges. Every Cauchy sequence converges. So this implies this, but every Cauchy sequence sequence in R is convergent. Okay, so let's say f and a converging to some value fa. Okay, now also f and x minus f and a, okay, is less than, okay, epsilon by 2. Okay, for all for all one. I made a mistake. This is here. So what is this actually? This is less than. What is this? Fn minus fm x minus fn minus fm a. Okay, absolute value. Okay, this quantity is less than this. Okay, less than this. So what does it mean? It means we also have this one fn fn minus fm x minus fn minus fm a less than epsilon by 2 for all and m greater than m. So this implies, so what can I write this? I can write this in a different form. How? What is this? This is equal to f and x f n minus f fn minus fn x minus fn a. Okay, minus fm a minus, sorry, this is x. This is x here. Less than epsilon by 2 for all m and n greater than m. Okay. So what does it mean? It means, what is the meaning of this? What is the meaning of this? This implies this sequence fn x minus fn a is Cauchy in R. Okay, in R. Okay. So this implies Fn x minus Fn a converging to some gx. Okay, gx. So this implies, so in that you take here g. Okay, so this is converging to g. So this implies, so this implies Fn x, but this is converging to, but this is converging to, Fn is converging to, Fn is converging to Fa. Okay, so let's write it properly. So this implies this is converging to G, but Fn A is converging to Fa. So this implies Fn X converging to Fa plus Gx. So I am saying it Fx. Okay. So this implies Fn is converging to F point wise on AB. Okay, on AB. Okay, and we know every Cauchy sequence is a bounded. Okay, this is converging to F point wise. Okay, now I'm going to back. So from I'm saying the above equation 1. Above equation. From 1, what we have? From 1, we have Fn minus Fm Fn A minus Fm Fm A plus Bfn minus Fm AB is less than epsilon by 2 for all n greater than n and m greater than capital M. Capital M. Okay. Now, but this is so what does it mean? Fn A minus Fm A plus SP F is less than, because this is less than epsilon by 2 for all n and m greater than capital M. Because P for any partition P, SPF is always less than variation of F. We know it. Okay. So it means, so what is, suppose I am taking this partition F and A sorry, FMA. So what is the partition? I goes to 1 to n, fxi minus fxi minus 1 less than epsilon by 2 for all n and m greater than capital M. Okay. So partition in x0, x1 up to xn is equal to b. Okay. Now Fn is point-wise converging. So letting, so here is what. So I have made a mistake. Let's correct it. I should write here. Summation I goes to 1 to n Fn Fn xi minus Fn minus Fn xi minus 1 that is less than epsilon by 2 for all n and m greater than capital M. Letting m tending to infinity, what we get? We get, because function is tending to fx, so this will be Fn a minus fa plus summation I goes to 1 to n Fn fxi minus Fn fxi minus 1 is less than epsilon for all n and n greater than capital N. Okay. Because Fm x is tending to fx for each x. Okay. Point-wise convergence. So that is why we are getting this. Okay. Now, what is this? This implies Fn a so I am taking limit. So I am taking limit, so it will be less than equal to. So I can write this plus summation I goes to 1 to n Fn fxi minus Fn minus fxi minus 1 that is less than equal to epsilon by 2, but this is okay for all n greater than capital N. Now what is this? What is this? This SP of Fn minus f that is less than epsilon by 2 for all n greater than capital N. Okay. So this implies Fn minus Fa plus supremum P belongs to rho AB SP Fn minus F is less than epsilon by 2 for all n greater than capital N. Okay. So because this is a non-negative quantity, so this implies, let's say this is equation number 2. This implies supremum P belongs to rho AB SP Fn minus F is less than epsilon by 2. That is finite for all n greater than capital N. Okay. So I can take capital N here, capital N, because this is true for all n greater than equal to capital N. So this implies SP Fn minus F that is less than epsilon by 2, but this is finite. So this implies Fn minus F. So this implies supremum P belongs to row A, B, S, P, F, N minus F exists in R. So this implies Fn minus F is function of bounded variation. Now Fn and Fn minus 1 both are functions of bounded variation. This implies Fn and Fn minus 1 are functions of bounded variations. Bounded variation. Now, so this implies their difference Fn minus Fn minus F, that is F, is also function of bounded variation. Okay. Also function of bounded variation. Now from equation 1, I have shown that Fn converging to F, if Fn is Cauchy, it converts to pointwise F, and F turns out to be function of bounded variation. Now from equation 2, what we have? From, sorry. Now from equation, we have already taken equations 1 and 2. So let's change it. So let's check it. So let's check it. So this is equation number. Let's say this is equation number 2. And change accordingly. Sorry, let's say equation number 3, because 1 and 2 we have already taken in this practice set. Now you write here 3. Now you say equation number 2 here 4. Now from equation number 4, we have, what was the equation number 4? Let's check it. Equation number 4, this. This is, okay. Fn A minus Fa plus supremum P belongs to row A, B, S, P, Fn minus F, that is less than equal to epsilon by 2 for all n greater than. Now Fn minus F is function of bounded variation. So then, and this is finite. So what does it mean? It means, and what can I write this? Fn minus F, I can write this. And what is this? What is this? This is this. And what is this? B, F, and minus F, A, B is less than equal to epsilon by 2 4 all and greater than capital. Okay. But what is this? What is this? This is F1 minus F less than epsilon by 2 because whole this quantity is equal to this. So this implies F1 minus, but this is less than epsilon. Okay. So what does it mean? It means this implies that Fn converging to F. So this implies Fn converging to F in okay this. D. So this implies every Cauchy sequence in this space is this metric space is convergent. So this implies this metric space is complete. Is complete. So this implies is a complete metric space.